A very warm good afternoon on behalf of PG and Research Department of Mathematics, TG Vaishnav College. We welcome our participants for this afternoon session of day 1. It gives me immense pleasure to introduce our resource person for this session, Dr. Deepak Kumar. He pursued his postgraduate with computers in mathematics with computer science in Jamia Malik Ismail, New Delhi, and he completed his PhD in Dr. Ambedkar University, Agra. Under the guidance of Dr. Sanjeev Kumar, a mathematical study for tumor growth, the computational approach. He has over 20 years of teaching experience. Currently, he is a professor in Department of Mathematics, EFT, Manav Rachna, International Institute of Research and Studies, Deemed University. He has submitted the project development of mathematical model for tumor growth and its treatment strategies, resource development. He has also completed project implementation of pitch and stress modules for Hindi text of speech system. He has applied patent for diabetes test kit for infants through urine. He has given over 7 invited talks and chaired sessions. He has been attending many FDPs and he has guided 3 students for PhD. He has 5 books and chapters to his credit. He has about 21 papers in UGC listed journals and 29 in other journals. We are happy to have you at our midst, sir. I hand over the session to our resource person.
Thank you very much, ma'am. Okay. Now, I am Dr. Deepak Kumar. I am going to present here mathematical models of ordinary differential equations in biosciences. Actually, this is the subject biomathematics. Now here, what is the mathematics and biology? So at here, mathematics has always benefited from its involvement with developing science because each successive interaction always revitalize and enhance the field. Actually, quite often the term biomathematics is used for mathematical biosciences. Mathematical biosciences are mainly concerned with mathematical modeling in biology and medicine and deal with the area of biosciences which have already been mathematized. Since situations in life science are quite complex, we should have some insight into a situation before we attempt to formulate a new mathematical model. It is clear if mathematics does not become the part of new development in biosciences and it should involve in the biosciences, then mathematics will be not be a part of most important and
Excuse
exciting.
me, sir.
Hello.
Excuse me, sir. Can you show the PowerPoint in slideshow, sir?
Okay, okay. F5. Yes.
Thank you. Thank you.
Okay, ma'am. Thank you. Then this is the biomathematics. Actually, this is a combination of mathematics and biology. Actually, how it helped to reveal the possible mechanism involved in biological process, which is not explained with the help of biosciences only. Because in biosciences, there is some mathematical logic involved at there. So only mathematical background person can think in this way because which is not explained in biosciences to help and interpret the revealed contradictions and incompleteness of data. If our data is not completed, then with the help of mathematical techniques, we can complete the data or some parameters which are not calculated. If in any case, through a laboratory experiment, if we do not have the complete data, then with the help of mathematics, we can see the data and we can calculate the data. Then it is to help and confirm the hypothesis only. With the help of statistical techniques, if we have some data, then with the help of these mathematical techniques, we can think if our data is not appropriate, uh, we can check the data. Our data is in going the right direction. What are the our in our mind? to for the purpose of the work. So with the help of mathematics, we can see our hypothesis is going in the right direction or we are going the wrong direction. And it can predict the performance under untested conditions only. Because in as per if we want to work on a drug. So we if a person, if in medical sciences want to test his or own drug in an animal or human beings, so he has to complete some legal formalities. So to satisfy the persons, these are the our outputs of this drug or combination of drugs. With the help of mathematics, it can be designed and we can create a model. Then we can convince the people this model will work and our drug will work on this particular disease, and to supply information about the values of experimentally and inaccessibly parameters. There is some confounding variables also. If we know the dependent and independent variables, then with the help of mathematics there is some confounding variables also which may affect the independent or independent variable. So with the help of mathematics, we can see them confounding variables also, which is not we can see directly, but they have its impact on the output to suggest the new hypothesis and stimulate new experiments. Actually, what is the benefit of mathematical modeling? Without doing an experiment in a lab or in at human beings, we can see our results. This result will be beneficial for the mankind or not. So in the field of medicine, mathematics play a very important role. In biochemistry, we can see biochemistry involve the mathematics also, because with the help of I had done work on tumor modeling. In the tumor, almost people or all the medical sciences doctors provide the adriamycin, but adriamycin has a lot of side effects. So how the adriamycin will work and how can make the better medicine for the tumor? So then people try to make the combination of other drugs with adriamycin. Then how will be the effect of adriamycin with the combination of other drugs? It can be seen with the mathematical modeling also. Then first thing is, what is mathematical modeling? Mathematical model is the formulation in mathematical terms. Actually, the question is that how will we make a mathematical model? Mathematical model, a person can design a mathematical model with his or her life previous experiences. If a person has done some work in his own subject, he don't have the mathematics background, but he can think, okay, how the variables are changing, then we can apply which type of mathematics so we can see the results. So mathematics modeling is a process of deriving such formulation. There is a formulation. Now mathematical process. First we read the real world situation. What is the real world situation? And then we will interpret this real world situation to modeling world and then formulate. Formulation is the most important. Formulation, some people are working in the real analysis and some people are working in new developed techniques in mathematics like fuzzy set theory, revolutionary algorithm. So it is depends on the person thinking, how is he thinking to make his results for the benefit of mankind. Now here there one subject, operation research of mathematics. That's the most important subject, or optimization techniques. So this subject is also help to manage the hospital and instruments and the diet related plans of hospitals. And stochastic modeling helps for experiment conclusions in medical and paramedical sciences. So these are the important things at here. Then how will we make the models? Stages of modeling. First, ask the question. What is the question in the uh, mind? And then we choose the mathematical approach. We can take the help from the differential equations, we can take the help of our stochastic modeling as per our experience of mathematics. Then we formulate the model, then we solve the model and then validate if possible. Sometimes it is not possible, we check our results in the real life situation because that result is not matched with the actual what happened. So there is some problems which we cannot validate our result because it may be possible. And then answer the question. If our answer of the question is match with the real life situation, then it shows that our model will work. If this is not possible, then we can see and we can check our model with some other techniques or with the conceptual theories and with the discussion with the people. Then there is the limitations of mathematical model. It is not mandatory that our mathematical or all mathematical models are correct, and it is maybe some unrealistic model may fit the data. It may be possible our answer will match with the real life situation, but we when we apply this model with the in field, then it may be that it will not work as per our desire. So the simple model are easy to manage, but complexity is existing in the model. So first we try to make the simple model, and then step by step we should uh, increase our model complexity. Then realistic simulation require a large or hard to obtain parameters, because in realistic situations we have to apply large data on our model and then we will say the situation. What is the situation? Now I'll come to our differential equations. Differential equations is a very simple term. If we study this differential equation in the 12th standard, then what is differential equation? The fundamental theories is this: an equation which contains differential coefficient is the differential equation. So at here it is derivative or rate of change. That's as in physics. The differential equation will apply everywhere where is the change of independent variable and with respect to the dependent variables. Then the famous Norwegian mathematics says among all the mathematical disciplines, the theory of differential equation is the most important. There's a Marius Sophus, live mathematician. Then he says many of principles in science and engineering concern relationship between changing quantities. Since rate of change of represented mathematically by derivative, it should not be surprising that such principles are often expressed in terms of differential equations. Now here I'll talk about the population model. This is the very simplest model of the differential equations. It depends on the birth and death. So if we talk about, suppose B is the birth rate, this is dn by dt, and D is the death rate at here. N is the size of population. Then its result solution will be n is equal to n naught e raised to power 80. N naught is the here initial size of population. Now you can see here this equation we can get with the help of mathematics. This is the first principle of derivative. Then you can see this is the very simplest model. We have birth and death. If birth is more than that, then this A will be positive. If birth is less than the death, then A will be negative. If our A is positive, means birth rate is more than the death rate. If our A is negative, it means that death rate is more than the birth rate. Then size of population will decrease. If it is positive, then size of population will increase. Now here, population model are used to determine the maximum harvest of agricultural, and it can to understand the dynamics of biological invasions and for environmental conservation. Then population model, it is first stage of population model. Then population model depends on these other terms also, because our population factors are here emigration and immigration also. Natality is the scientific name of birth rate, and mortality is the scientific name of death rate. So population depends on these terms. So how will we include these parameter in our population simple population model? Then our model will become dn by dt is equal to b minus dn plus I minus e. So I is represent the immigrants and e is the emigrants. So this will be this is in this model we are including the immigrants and emigrants people also. Now we'll come to the this is the model. Then we'll come to the logistic model. Logistic model is most important model because in 1930 a scientist Pierre Francois and what sort of equations you have seen in the mathematics already. Then what is logistic equation? Because simple model can produce the exponential growth, but we know that exponential growth is not sustainable. So per capita growth rate does not change even population gets very large, but it is not true. In logistic model, per capita growth rate gets smaller as population approaches maximum size, because level of eventually and approaches its carrying capacity, because it's a limited resources. If resources are limited, then it is very much true the population of that particular town or particular country will not increase. It will be it has a maximum limit. So this logistic model produce this concept at here. So decreases population well and increase uh, as per the resources. Now here, this is the solution of this model. This is n is equal to and not k e raised to power kt. So this is the logistic model which present the carrying capacity. What is carrying capacity as here? The constant K is carrying capacity of the environment, which is usually determined by the available sustaining resources. So, the solution of this model graphical representation is when it's depend on K. If your K is at here, logistic population growth, not that quality of two cases and not is K by 2, then you can see the result. And if K is greater than and not, then your population will decrease automatically. So this K is the carrying capacity at here. Then we can see the some modifications or some advancement in logistic models also. So the differential equation is used to model population that are subject to harvesting model. Harvesting model means some if we see we have the logistic model already developed, but if in a pond we think the population of fish being caught at a constant rate, means the population is decreasing with a constant rate. So this model is known as the harvesting model. Actually, this is the logistic model. And then one more modification in the logistic model, that is sparse model. Then we included the 1 upon m divided by n. So this is the sparse model. This is scattered model. Uh, if our population is scattered, then we can apply this model. So these two models are actually the logistic model. This is the advancement of logistic models. Then here, population model may depends on the age also, because the birth rate and death rate, birth rate is not depends on the elder people or juvenile, actually means those are ages are less than 18. So these two age people not increasing the population. If we increase this parameter, because it is the age dependent thinking also. So this model will work. This model is actually A is the age of range of the age of the people. A plus del A, BA is birth rate, D is death rate. Then our model will become the partial differential equations. Reason behind that, because our model now depends on not only on time, it's depend on age on also. So these are the two independent parameters which can affect the our size of population. So this result you can see it here, uh, 10 to 50. So I should think this is the age the people are growing, but 10 to 70 there is an age which is not at there. They cannot increase the population. Now I'll discuss about the delayed differential equation. How the model population model will become the delayed differential equation model. Because a delayed differential equation model is the differential equation where the time derivative at its current time period on the solution and possible its derivative at the previous time inspected of simple initial conditions, and initial history function needs to be specified. If this function needs to be specified, the quantity of called the delayed, or it is time tag. In delay differential equation are more generally the functional differential equation. The past expert at its influence in a significant manner upon the future also. Now here the delay differential equation, retarded means the delay or slow down, means our time different growth of the population is not continuous. It we cannot say our growth rate is always same. So it's depend on the time. What was the previous history? So we consider this concept in this differential equation model. Then you can see it here. This size of population n depends on t minus tau, and this tau is actual the time tag at here. Now we can discuss about the stochastic model also. When the simple population model becomes the stochastic model, because in stochastic modeling, it's depend on the randomness, and the randomness is here because this is there. Our growth rate will change time to time. So it is in the deterministic model, it was set. Our differential equation model says that this is set, but it is not actual. Sometimes you can see in a year birth rate is more than the previous year, or it may be that it may be less than the previous year. So birth rate or death rate may change. It may vary with respect to time. So there's a random changes at there. That's why you can see it here. This P 0t, 1t, these are the different changes in growth of the population. Now here we can see it here. We take this data and we can find the variance and mean of that data in functions, because this P is the probability at here. So this P can generate the probability generating function, and after this function we can see we can consider the exponential growth function, or we can see the, it's depend on our thinking, what we have in our mind, and how we can complete the model. So it is completely a stochastic model, because we have considered the random functions as here. Now I'll discuss the epidemic disease modeling. Epidemic disease modeling means the modeling which spread a person to person. So at here, we are very much aware in the last 6 months we have seen the COVID-19. We were facing this problem, and we have faced the lockdown in our life first time due to this pandemic. Then this COVID-19, we have read a lot of material on this concept. Then how the mathematics think in this area. COVID-19, we know that it spreads with sneezing, or infected person cough, and he exhale, and in air, that 1 second person can be infected. Now here, there is some technical terms are here. Endemic. An endemic is a disease that affects a large number of people within the community or within the population in a particular region. And it is pandemic if this epidemic disease is spread over multiple countries. That's why COVID-19 is known as the pandemic disease. And it is endemic is something that belongs to the particular location of the people. And initially it was a outbreak, because initial terminology of COVID-19 was the outbreak, because it started from China, especially from the person, no, especially from a particular place. So an outbreak is sudden increase in occurrence of a disease in a particular time and place. It may affect a localized group of impact upon thousands of people. Then mathematical epidemiology is concerned the quantitative aspect of the subject. Then we model building, estimations of parameter, investigation of sensitivity of the model and changes the parameter, and then simulations. The fundamental model, this is not the differential equation. We have seen the Arogya Setu. There were how the transmission rate is increasing, mortality rate is increasing, and recovery rate we have seen. So this is the simple formula of percentage. That is very fundamental thing of mathematics, which we done in our 8th standard, and we can see the growth of percentage of transmission, mortality, and a recovery rate also. Then second thing, this is the formula of the compound growth. So with the help of this mathematical formula, this is not all differential equation formula. This is, we apply the compound growth formula, because this in at initial stage of COVID-19, the infected person were growing. There was no chance of decrease of the patients. At initial stage, this function is only considered the growth function. Now, this was the graph of India date wise. You can see, and this was applicable when lockdown was managed. Now, the SI model. Now, this is the very famous thing, and we have seen in the news. First time I was very happy, because government of India was talking about the mathematical modeling, and especially SIR modeling. So I was thinking that's a very good. The people are knowing that mathematics can help to calculate, or we can see the results of, we can see the side effects, and we can see the changes in the growth of the patients. Their S is presented as susceptible, and I is infected, uh, particularly a disease. So suppose we are considering a bird flu or a something there, we can change the disease. This model we have considered for the avian influenza. So avian influenza in birds. So this shows that at here S naught is a size of population and I naught initially only one person is infected. On one bird is infected. So Si plus I is equal to n plus 1. Then this differential equation shows the ds by dt minus beta Si plus because this ds by dt proportional to the minus infection rate and the product of susceptible and infected. And you can see if the susceptible is decreasing, that's at the same thing, infected will increase because if 1% is changes from susceptible to infected, then it means that then you can see it here. This is the changes uh, on susceptible and infected person, and this these are the two simultaneous differential equations. We can solve it very easily, and we will come to the SIS model. You can see the previous model is SI model and this model is SIS model. Susceptible, infected, and then after infected again go in the list of susceptible. So this mathematical model was introduced by Kermack and Masendrick because they had done this work in 1927 on differential equation. So at here we can see there is a change infected person again decreasing and after infection phase they will go to the susceptible person again. This is the graphical presentation of SIS model. Now we can see the SIS model, the specification with the rate infection rate, because it is not mandatory that this model will work in the realistic data. So at the realistic data, we can see maybe this model will work. So we can enhance or we can increase or modify the data for betterment. Then this changes you can see at here di by dt beta n minus I minus beta I square. So this is the SIS model where infection rate we are considering. Then this is also the SIS model when carriers is we are including. The C is the carrier set here. Then this model will become susceptible, infected, and carriers. So this shows that at here we are including the concept or parameter of carrier also. Then we will come to the SIR model. After seeing the this is the SIC model, then SIR model. In SIR model, we consider the recovery also. You can see it here. The SIR model is the very good model to understand the situation of COVID-19 because there's a three terms were there: susceptible, infected, and recovered. So this model can show the future calculations or future thinking. What is the happening at the stages or different with respect to the time. Then we can see the mutations in SIR model. Mutations means is the alterations in SIR model because it is the exponential term is there. Like we have seen the delayed differential equation. So delayed differential equation is more realistic differential equations for the application in biosciences in epidemic disease, because we can see it here. Now you can see SIR model. You can see this is the SIR model. S is depends on T, I is also depends on T, and R is also depends on T. All are alpha beta for the real numbers. Then we can see we are adding the infectious delayed. Then our differential equation will become in this form because there's a delayed or time tag is tau at here. So this it minus tau is exponentially minus beta tau. So only this infection variable it, it's depend on not only t, this is t minus tau. So we are considering it here infectious delayed only. If we consider after infectious delayed, we can consider the delayed in recovery model also. Then our model will become SIR model. This is actually SIR model, but with the help of delayed differential equation concept, you can see it here. This is minus alpha SIT depend on T minus tau. So in recovery rate, this is was the beta I. So this is also beta T minus tau at here. Then we can see the incubation period also. Then our model will change automatically, and we can consider it here SITR model also, because we can see the treatment class and a recovered class. So S is showing it here susceptible class, I is showing it here infected class, and T is the those people are under treatment, and R is the showing the recovered class, those are recovered from the disease. So this differential four simultaneous differential equations ds by dt minus beta is di by dt beta si minus lambda I and di. D is the death rate at here, because infected person will die and those are going under treatment. So this is also we are considering at this time in infected persons, and then recovery rate dr by dt. So this is the advancement of the SIR model, and then we can see the solution of SIR model. This is a general solution and more very realistic situations. And it is not that this will result will match with the all the countries data. So we can think something else also, or we can enhance our model as per our thinking. Now, in COVID-19, some people have seen this model also. This is very interesting model, SI1T I2 R model. This model shows that here I1 is the person is infected a particular disease, but after admitting hospital, he got some secondary infection. So this secondary infection is showing at here I2. First person is infected and he got admitted, or he infected with other disease, and but in hospital he got some other infection also, like if person is admitted in hospital due to COVID, but in hospital he got infected with so this model will work in such situations. This happened already, and this is our one of the hypothesis. If such situation we face, then how will we develop our mathematical model mathematically? So these are the parameters here you can see, and then we see the first time in COVID-19 period SEIR model. So this is S is susceptible and E is exposed, because it was happened in NCR or Delhi, where people are infected with COVID but not exposed. But some people are exposed, not all people are exposed. So if there's situation, this model can be considered. If we have the data, then how will we tackle the data at the transmitting dynamic nature of epidemic disease? So we can see this model and we can apply the data on this model and we can see the results. And this is age dependent epidemic disease model also. Then it was most important at there. In Italy, it was seen that people are more than 65 age are dead due to corona, and age less than 10 was were children were dead due to corona. So in this situation, we cannot say our previous model will very successful. So we need to consider the age variable also and infection variable, because a aged person death rate was more than in the comparison of the young people. That's why our government of India decided in first unlockdown, then people more than 65 and children less than 10 will no go out from the home. This this model is required at that time. So I have seen this thing ds by dt, that's the tau, IAT. Only infection is depends on the age also. So this is the starting of this concept, and we can enhance this concept in our modeling approach also. Then I will come to the my previous work, that tumor cell division. That's the most important here. Then in the tumor cell division, we can see one of the simplest experiment in biology tracking cell divisions and bacteria over time. And the, what is tumor? Tumor is actually uncontrolled growth of cells. So it's a chain reaction. It is not that tumor will grow constantly. Sometimes we can see we feel some solid in our skin, but at after some time it dilute automatically. But if it is not diluted automatically, then it will become a cancer. And this is benign tumor is actually a vascular tumor where blood flow is not there. If blood flow at there, then we can see this is the angiogenesis type of tumor. Then it is the cell division, 2 to 4, 4 to more cells, and more to more cells. This is the growth of cells. And it is not the, it grows in the 2 power 2, 2 raised to power n. It is the only initial concept. But all the tumors are not grow in this type of concept. And when I discussed this thing, how the tumor is growing, so the medical science background people say tumor is growing in a cell line, but in mathematics we think that tumor is growing in a spherical shape. But it is not true always. All the tumors are not growing in the spherical shape, and sometimes the people think the hypothetical study that tumor growth is cylindrical or tumor growth is in other shape, elliptical shape. But it is the theory at there, because tumor cells are growing. So we can initial stage we can consider the tumor cells are growing. So we can take the fundamental model. The C is represent the concentration of tumor growth cells, and lambda is the proliferation rate. Proliferation in biological term is the cell division. Cells are growing 1 to 2, 2 to 3 to 4. So this is the proliferation. This is not apoptosis. This is not actually the cell death. Cells are increasing in numbers. If the uncontrolled growth of cells, is known as the avascular tumor. So this graph is the fundamental growth of the tumor, and this was the data. So in 125 days, you can see the growth of the tumor. And I had done this work at my PhD. So initial fundamental model tumor is this, and when this model will become in the form of partial differential equation. When we consider tumor is growing in a spherical shape. If tumor is growing in a spherical shape, it's depend on x and t. X is the radius of that sphere. So this C is depends on x and t. So this was the simple solution of this thing, and these were the parameters of this differential equation. Now the tumor cell density is growing in the 3D manner. So after you can see this was the presentation on 3D, 3 dimension. And most important thing at here, how will we solve the differential equation? Because if your differential equation comes in non-linear form, that's a very difficult to solve. So with the help of MATLAB, we can see easily our differential equation is solvable or not solvable. So how will see that we can go to the numerical methods also. Numerical methods can give the results, but it is not sure that our result will match with the actual realistic situation. So this is the uh, very simple mathematical commands on MATLAB. Solve means differential equation. You can see the solution. So this is the linear differential equations, and we can see the higher order differential equation solutions also. And in simultaneous differential equations, there is some commands I have shown this x and y. These are the two simultaneous differential equations. It can be solved with the help of command solve in MATLAB. And this is the second order differential equation where the you can see this is the d2y by c square y, and y naught is 1. This is the initial condition, and dy naught is 0. So these are the initial condition which we have given to the software MATLAB, and this differential equation can show the solutions. And the most important thing, I have shown one program at here. This is the solution of SITR model. So with the help of MATLAB, you can see this was the simplest program, and if we run the program, we can see the results. And this is seen the complexity of biological sciences makes interdisciplinary involvement that is essential for mathematics and biology also. That opens the new paradigm of research, because the biologists or medical science background people don't know the concept of mathematics, and mathematics people do not know how the biological concepts are working. But if the uh, person want to do work, then mathematics can help in biosciences, because it is the most important thing. The bioscience is the more realistic sciences which is related to the all human beings. So biomathematics is today a growing and essential adjunct to the further development of the biological and medical sciences. If it is to play its proper role in an efficient and inspiring way, it must be planned and organized on a scale according to the importance of its contribution. Now, initial days, we have seen one more branch is growing very fast, biotechnology. So, this biotechnology is what? When biosciences people seen there, they if they work with mathematics background or some technical background, then results of this uh, branch will be more helpful for the people. That's why nowadays biotechnology is a very growing field for research in biotechnology. Not only that, the mathematical people are need, and only not only the biosciences people are need, or the combinations of technical background people and biosciences people will create some model or some advanced studies for the benefit of the mankind. Now, I have seen and All India Medical Institute of Science, New Delhi, has the Department of Biophysics, and the in the Department of Biophysics is very very interesting, and they are working on very realistic modeling, and it helping the people. Now, thank you very much. I think these are the references of this presentation. Now, thank you very much, sir. Hello. Yes.
Yes, sir.
Yes. Thanks
Yes,
very
sir.
much. Presentation is over.
Okay, sir. I think
Okay.
we have one question, sir.
Yes,
Would
yes.
you like to answer? Which model is best for COVID 19?
Actually, if you want to do work on COVID-19, so then I think the stochastic modeling is now is very developed, because at initial stages, deterministic model work, but with respect to time grow, because randomness is there. So if you want to consider the randomness, then it is mandatory that we have to go to the stochastic modeling.
So there's one more question.
Yes,
dA by dt is equal to Ka. That is, A is equal to C into exponential to the power of Ka, e power kt, isn't it, sir? Can
yes.
we use this method to calculate the infection spread? What is the need for SIR model and other? How this
We
model differs
actually
from the
is
other tools?
this is the actually this model is the first a growth model, dA by dt, because if mathematically you think it, this is modeling dA by dt. We are seen there like there is changes in A with respect to time t. So this model is with a very simple model. We can see the infection spread, but this is only the exponential growth. But in case the growth is not always in exponential manner. So this model, we can go to the SIR model first, and as per our available data also. If we have the lot of model in our mind and we don't have the data, then how will we interpret that data? So because if you want to make a model, then before making a model, it's depend on our parameters and data also. What parameters in our hand, that's the most important at there. So we can make a model according to the available parameters first. Hello, ma'am. You got my
Thank you,
point?
sir. Sir, yeah, yes, sir. There's one more question, sir. How to find the residual error in model equation?
Yes. These are some solutions technique. These are the this error we can see if we have the realistic data and the results also. Then we can find the error. And these residual error, depends on the solution technique. a lot of techniques are growing in the mathematical modeling. So you can it's depend on the our solution techniques.
Okay, sir. There's one more question. Why don't we
Yes.
consider the tumor growth in Fibonacci series? Is it sensibly right?
No, we cannot say because tumor growth is not always in the manner of because it depend on the environment also. All has been noticed if a person is infected with tumor and he change his environment and with the and diet plan and medicines, so it is not mandatory that it will work on the Fibonacci series. Initial stages you can, but it is not always. So I have seen there when I go to the AIDS department. So the medical science background people not easily convinced with our concepts. I face this problem at lot of time. So first I have shown them some journals paper like mathematical biology or bulletin of mathematical biology. These were the very famous journals. When the people seen these journals results, they were surprised how the mathematics modeling work with the biosciences. But after some time, they have noticed that differential equations, not only mathematical model, help there because they have some thinking at there. According to their every cells have their own nature, stem cells, and repairing mechanism of the all the cells are different. You got my point? Because a
Yes, sir.
person is having tumor, which part in our body? Medical first indicate this thing. Okay, which part of body is infected with tumor? Then they will go to the study and which model will apply. So it is after discussions with the medical background people or biosciences people, we can which model we can apply because modeling is the secondary thing at here. First thing is the concept. What is the biological concept? And we are working on the biological concept. So first we have to see the biological concept and discuss with the biological background people. Then we think according to our mathematical modeling. Then how will we make the model?
There's one person, Rajesh Agri, has asked for the reference book for ODs.
Ordinary differential equations.
Yes, sir.
Yes, yes. So ordinary differential equation modeling actually J.D. Murray of mathematical biology book is very good. For J.D. Murray, people considered the J.D. Murray considered the differential equations model almost. And second book, I can see that the J.N. Kapoor is an Indian author, and this book is very fantastic. I can show you a book, mathematical modeling for biology and medicine. This is a very good book. First, you go to the J.N. Kapoor book, and then go to the J.D. Murray book. Then you can understand the modeling approach. When in 1 or 2 months you complete these books, and then when will you about the mathematical modeling, biological concept, then automatically the thinking will develop.
Ma'am, any other questions? Good afternoon, and all the sessions are very relevant and nice to listen. These are comments, a few comments, like so many of them have said very nice presentation. So I think
Thank you
there's
very much.
more questions,
Thank you
so
very
we'll
much.
just be, thank you. Thank you.
Thank you very much.
So I request
Thank you.
Miss K. Kalpana. I request Ms. K. Kalpana, Assistant Professor, PG and Research Department of Mathematics, TG Vaishnav College, to thank our speaker.
Good afternoon to all. Gratitude is the healthiest of all human emotions. It is my privilege to propose vote of thanks on this occasion. First, I thank Almighty for showering blessings in making today's session a successful one. A warm and sincere thanks to our resource person, Dr. Deepak Kumar, Professor, Department of Mathematics, Faculty of Engineering and Technology, Manak Rachna International Institute of Research and Studies, Faridabad, for readily accepting our invitation amidst his busy schedule and enlightening everyone with his thought provoking lecture on mathematical models of ordinary differential equations in bioscience. Thank you, sir. A special thanks to all the enthusiastic participants across the country who made this national conference a grand success. Thank you all.
Dear participants, our next session is at 3:30. Please join us.
sorry. Camera off பண்ணிருக்கீங்க. Okay, just 2 minutes வந்து இது பண்ணிட்டு ஜாயின் பண்ணு. ஸ்க்ரீன் ஷேரிங் ஒன்றும் ப்ராப்ளம் கிடையாது. இல்லை வந்து உள்ளே வந்துட்டு நீங்கள் அதுக்கப்புறம் 3:30 கரெக்டாக சார் ஜாயின் பண்ணீங்க. இல்லை ஜஸ்ட் இப்போ வந்து உள்ளே வாங்க சார், கேமரா ஆன் பண்ணிட்டு உள்ளே வந்துட்டு அதுக்கப்புறம் நீங்கள் 3:30 ஜாயின் பண்ணிங்க கரெக்டாக வந்துங்க. இல்லை சார், என்ட்ரு ஆகிட்டீங்க நீங்கள், கேமரா ஆன் பண்ணிவிட்டு ஜஸ்ட் இது பண்ணிடுங்க. Good afternoon, sir. Hello, sir. Good afternoon.
Yes, sir. Good afternoon. It's audible?
Yeah, audible, sir. Audible, sir.
Yeah.
Sorry, are you able to share the screen, sir?
Yeah, 1 minute.
சார் அது கொஞ்சம் இருங்க மேடம். Okay, sir. Share ஆகுது சார்.
Is it my PDF is visible, sir?
Yes, sir. Visible and your voice is audible. No issues, sir. We have 3 more minutes, sir.
Good afternoon, all. As we move on to last session of the day one, it's my privilege to introduce our resource person for this session, Dr. S. Dinesh Kumar. He completed his postgraduate in Anna University and did his doctorate in Vishweshwara National Institute of Technology, Nagpur, in numerical methods for solving singularities, perturbed delay differential equation with large delays under the supervision of Dr. Pramod Chakravarti. He has teaching experiences in various institutions. Currently is working as an assistant professor, Department of Mathematics, School of Advanced Sciences, VIT Vellore. He has 8 publications to his credit and has attended many conferences. He is also well versed in computer languages. It is an honor to have you here, sir. I hand over the session to the resource person.
Thank you, ma'am. I think it's audible, right?
Yes, sir. You're audible, sir.
Yeah, my screen is visible.
Yes, sir. Screen is visible, sir.
Yeah. So, and again, good evening. My presentation is on the topic like higher order fitted operator numerical scheme for singularly perturbed delay differential equations with large delays. Okay, so people are working on small delays and going for the large delay. So, a more general type of differential equations, which also called as a functional differential equations. The simplest functional differential equations called a delay differential equations. Delay differential equations are similar to ordinary differential equation, but the evaluation involves past value of the state variables. The solution of the delay differential equation therefore required knowledge of not only the current state, but also the certain time which has occurred in the past. So what is meant by singularly perturbed delay differential equation? Whenever you have a differential equation which is multiplied by a small parameter for the highest order degree, then the problem is said to be a singularly perturbed delay differential equation. So that is the definition is given here. The singularly perturbed delay differential equation is a differential equation in which the higher order derivative is multiplied by a small parameter and involving at least one delay term. So it's called as a delay differential equation with a perturbed parameter. What are the applications of these type of equations? So every control system which involves time, so the delay differential equations plays an important role, and also in modeling of various practical phenomena in bioscience and control theory, and also used in transport problem where the time is going to occur, gestation times, periods, and also it's used in duct therapy, infections of problem based on the bioscience, and also immune systems. Okay. So where you are going to play with respect to a time, or the past history, where I can use the past history to my future problem. Okay, so for that type of problems, we use a modeled problem according to a delay differential equations, and we find a solution for this. So these are the application part of delay differential equation, where we are going to use it in the large scale, also in respiratory system, tumor growth, neural network, statistics analysis of ecological data, where you have the past values. And these are the applications of differential equation, like delay differential equations. If you have a singularly perturbed delay differential equations, so it has, again, it's a small parameters multiplied to a differential equation with a delay term. These modeling problems and has a variety of biological influence on this, on optically bistable device, description of human pupil reflex, variety models on various form of diseases, and variation problem in control theory. So these will give me the phenomena idea, where you can have a case study on this modeled problem, and you can predict the solution for the given problem. So in this, what we are going to see here is the singularly perturbed delay differential equation. We are going to see a second order differential equation with a delay term and also a parameter term second, and we are going to look into an higher order derivative. So in this, work in this, we are going to look into a fitted operator finite difference scheme, that is nothing but the numerous method. For a singularly put up delay differential equation is used for the reaction diffusion type. There are two types of equations commonly we are looking into it. One we call it as reaction diffusion, and another we call it as a convection diffusion. So these are the two problems. So we are now looking into a problem called reaction diffusion problem, and the derived scheme is almost fourth order accurate, and the computational work is carried out to find the solution for the given proposed method. So we have a boundary value problem of reaction diffusion term. You can see a problem where this is a delay term, this is a delay term, and minus epsilon y double dash of x plus a of x y of x plus b of y of x minus 1, this is a delay term, is equal to f of x, where this problem is valid for the interval 0 to 2. You can see a second order derivative is multiplied by a small parameter epsilon. This epsilon value is very small, where it lies between 0 and 1, and you can see you don't have a term called y dash, a single derivative is missing. So we call this type of problem as a reaction diffusion type. If you have a y dash, then we call it as a convection problems. So subject to the boundary conditions, you can have a boundary condition y of x is equal to phi of x with the past history, because the delay term is there. So we have the past history like minus 1 to 0. We have the condition at boundary, we have y of 2 is equal to beta. Okay, epsilon is very small parameter, and we are giving the conditions for the coefficients of y of x and y of delay term. Okay, y of x minus 1. Okay, a of x is positive, b of x we are considering negative, and a of x and b of x will be greater than 2 alpha. Alpha is a very small quantity which is greater than 0, and phi is a smooth continuous function over the range minus 1 to 0, and beta is a constant. So this is the modeled Dirac problem of reaction diffusion type. So for this problem, what we are going to do is we are going to study a method or already existing method. A finite difference scheme is used for this method, fitted operator finite difference. To tackle this delay, we are using a fitted operator scheme, fitted operator parameter to handle this delay, and we are going to use a finite difference scheme for the given problem using a numero method is constructed. So once the numero method is used for the scheme and we having a fitted difference scheme, we are using a Thomas algorithm to solve the problem. So after solving the problem, we are comparing the solution with the existing solutions or using my double mesh principle. So this is the problem. So what I say here in this, according to this problem, is the sense like this is my history condition. Y of x is equal to phi of x is my history problem. History means in the past value. So this, according to the given problem, from 0 to 1, 0 to 2, what I'm going to do, I'm going to divide the problem into two intervals like 0 to 1 and 1 to 2. Then I'm going to use it. So you can see my problem is rewritten as two classes, from 0 to 1 and 1 to 2. So from 0 to 1, the past history is used here because it valid from minus 1 to 0. So I'm using a past history to given problem. Then for second L2 of L2, I'm using my given condition 1 less than or equal to x less than or equal to 2 for the second problem for the range 1 to 2. So I have a for a given differential equation is rewritten as these two differential equations, L1 and L2. I'm going to solve it for 0 to 1. After getting the solution for 0 to 1, I'll use it for 1 to 2. Then what I do, I combine the solution for the entire range. Okay, so these are the things what I'm going to get. I'm giving the solution y of x exhibit between the boundary layer x is equal to 0, 2 and 1, interlayer 1. So after solving for 0 to 1 and 1 to 2, the solution will be, I'm considering y of x is the solution of the problem, y0 plus y1 plus y2. Y0 is nothing but the solution at the x is equal to 0. Y1 is nothing but the interlayer x is equal to 1. Y2 is nothing but at x is equal to 2. Okay. So I'm going to show some analytical result for the given problem where it satisfies the principle for continuous case, whether solution exists. I'm all using this lemma, using the condition for this problem. I'm going to give a prediction on this. So this is my lemma 1, where I'm going to use this lemma to my existing results. So my analytical results are given here. So I'm checking the maximum value of this continuous functions. Lemma 1 and lemma 2 shows the function is continuous and the solution is exist. And lemma 3 says the above equations predicts analytically up to which order of convergence. So these are the theory where is the existence is going to be happen. So I'm going to find each solution at x is equal to 0, x is equal to 1 and x is equal to 2. So these are the theory like described here. You will be getting the source, how it is done, general principle. Very important lemma. So I told you y of x is a solution. Y of x is equal to y naught plus v naught plus w naught, and we're taking y naught is nothing but the solution at x is equal to 0. V naught is nothing but the solution at the left hand side boundary, that is nothing but at 1, and w naught is nothing but at y is equal to x is equal to 2. So after combining at x is equal x naught, x is equal to 0, x is equal to 1 and x is equal to 2, after combining all the solution, that is nothing but the solution for the given delay differential equation y of x. Okay. So y naught, we call it as a reduced problem in the sense where the epsilon is very small. So as epsilon tends to 0, my y double dash will be reduced, and we call that as a reduced problem. So I'm checking whether that is valid for the given problem or not. So these are the principles what we are doing it for the given. So how the solution is used. So I'm going to use my numero method for the given problem. I already told you. So I told like after setting my epsilon as 0, epsilon tends to infinity, and epsilon tends to 0. So my epsilon is very small quantity. So it's very prescribed like. So when for the given differential equation as epsilon tends to 0, my problem will be reduced like this. So that the y double dash prime term won't be there. So this is my given differential equation. So in this, if epsilon is 0, what happens? This term is vanished. So if this term is vanished, I will be getting y of x is equal to f of x minus b of x, y of x minus 1 by a of x. That is a term what I written here. That is a term what is written. So which does not satisfy the boundary condition because we have y of x. So y of x is nothing but the reduced term, what we call it here. So what will be to find the value of y at x is equal to 1? This is nothing but y naught. So y1, suppose I take this value as a gamma, the solution of the reduced problem. And so what happens? My given problem is divided into two interval. One is 0 to 1 and one is 1 to 2. So to solve my given problem, I need a two initial boundary value problem, boundary condition I should have. So for 0 to 1, my subjective conditions will be, one will be the history function, that is nothing but the past value, and at y is equal to 1, because I'm solving from 0 to 1. So the reduced problem will give me the boundary value at x is equal to 1. So that is nothing but y of 1 is equal to gamma. Similarly, for the second condition, the L2 is nothing but with respect to 1 to 2. I'm solving from 1 to 2. So y of 1 is equal to gamma 2, y of 2 is equal to beta. This is already given in the given problem. So I make my problem to reduced using the principle of, because epsilon value is very small, epsilon tends to 0. So my problem is reduced and I'm finding the value at y of 1. So the now I got the value, exact values where I'm going to solve it between 0 to 1 and 1 to 2. Now I'm getting this 8 and 9, equation 8 and 9. You can see that from 0 to 1 I solve it using my numero method. Similarly for 9, from 0 to 1 to 2 I solve this equation. So I combine this will give me the y of x, that is the solution. So again, one more difficult part in the sense is you can have your epsilon here. This epsilon is very difficult to handle. So to handle this epsilon, we are using a fitted parameter. So we are using a fitted parameter. We'll see what is a fitted parameter. So fitted operator is used. The sigma, instead of the sigma is used multiplied with respect to epsilon. To handle this epsilon, we are multiplying a parameter called sigma. So The given problem is, this is the generalized given problem. So sigma is nothing but the fitting factor which is to be determined. Okay, so what you are going to do is a generalized. Now we are going to get a fitted finite difference scheme in the form of y of yi plus 1, yi minus 1 in the tridiagonal system format. So for my given differential equation, what I'm going to do is I'm going to divide the given differential equation into two segments. 0 to 2 is divided into two segments, like 0 to 1 and 1 to 2. After getting from 0 to 1 and 1 to 2, I'm going to solve the between the range, and I'm going to combine it. Okay, so that is a theory we are given here. We divide the interval 0 to 2 into 2n equal parts with the step size h, mesh length is h. Let 0 to 2 is divided into equal parts. X naught x1 is equal to xn. So x naught is nothing but the initial value, x2n, that is nothing but I'm dividing into 2n equal parts. 2n is equal to that end point 2 with the mesh points, and xn, the in between value will be equal to 1. That's the idea we are going. One is divided into two problems. One is 0 to 1. Sorry, 0 to 2 is divided into two problems. 0 to 1 and 1 to 2. So 0 is nothing but x naught, x2 is nothing but end point, x21 is nothing but 2, xn in between point is nothing but 1. Okay. So this is my form. So I'm writing the given differential equation in this form. If I take this form as a positive one, this will be a of x, y of x plus b of y, x, y of x minus 1 minus f of x will be sigma into gamma, sigma into y double prime. So I'm writing that conditions. Sigma is nothing but the fitted factor, y double prime is equal to g of x. So g of x will be minus f of x minus a of x, y of x plus a of x, y of x plus b of x, y of x minus 1 will be my g of x. Okay. So for using the notations, yi is nothing but y of xi. So using the given parameter, and I use my numero scheme for the given problem 10. For this problem, at the each nodal point I'm constructing for x is equal to xi, my each form will be y double prime of xi plus a of xi. A of xi is we consider as a constant, so I can take it as a suffix ai. Y of xi, that is nothing but yi plus bi y of xi minus 1. So this y of xi minus 1 is a delay term. For 0 to 1, it will use my history function, that is nothing but 5. From 1 to 2, it will use my previous value of 0 to 1. So after using my numero method and combining in this, so my difference scheme will be like this. So you can see my scheme. So after using my numero method, numero finite difference scheme for equation 10, this is my equation 10. For the each nodal x's, my scheme will be like this. You can see my scheme. This is in the form of ai, yi minus 1, yi minus 1, yi and yi plus 1. These are the coefficients of yi minus 1, yi and yi plus 1. Okay, so while you have a coefficients of this, so what can you say about this coefficients is like this. If you consider this is ei, gi and fi, this is in the form of tridiagonal system. Okay, so this is the tridiagonal system, and equation 12 you can see this is also from for this equation using the condition 7, the above scheme can be rewritten as this form. For I varies from 1 to n minus 1, from the range 0 to 1. This is the scheme. We are using a history function for this. You can see here 5 will be there. And for n plus 1, up at n you know what is the value, n plus 1 to 2n minus 1, this will be the scheme. It will use my previous value. So the above matrix, the above problem can be written in the ay is equal to f format. A is nothing but these values, whatever it's as a diagonal, subdiagonal and superdiagonal. So that is given in the form of a vector, like where it represents as a diagonal system given in the matrix form. So using, you can see here what is fi, fi to I, and the conditions are given here. So this given system can be easily solved we have a lot of algorithm to solve the system. A well-known algorithm, what we are going to use is like Thomas algorithm to solve a problem. So using some Thomas algorithm, we are going to solve this given problem, and we are going to find the solution for this. Okay. So here one more task is that we want to find the value of this sigma. Sigma is a fitting parameter. So the matrix A, using the matrix theory, we are finding the sigma. So any matrix theory can give you the prediction how to find. If you have a matrix AY is equal to F, A is a matrix of system, and Y and F are corresponding vectors. Now to calculate that sigma from the given problem. So the sigma is calculated here. So the system A, matrix A of the system 14, 14 is nothing but AY is equal to F. So it's calculated and sigma is calculated. And after calculating the sigma, you can substitute in the given problem and you can find the fitting parameter. The fitting parameter is this. I'm using a notation xip. Xip is equal to e power minus rho h plus 10 plus e power rho h by 4 sine h square of rho h by 2. So rho is nothing but square root of a by sigma. So this is my fitting parameter. I'll use it in the sigma and I'll solve the problem. Okay. So using this fitting parameter, I substitute in the formula. So we solve the above tridiagonal system for this. So once you get the sigma, you are going to substitute in the equation 12. Equation 12 is nothing but the tridiagonal system, what you're getting yi minus 1, yi plus 1. And we solve the above tridiagonal system along the boundary conditions by using Thomas algorithm. So for 1 to 2, the system is solved. Similarly for n plus 1, from 1 to 2, this is nothing but 0 to 1. This is nothing but 1 to 2. 1 to 2 means n plus 1 to 2n minus 1. The above scheme is solved. So we solve the above tridiagonal system along with the boundary conditions. Yn, you know Yn, xn value, Yn at sigma gamma, and y of 2n is equal to beta by Thomas algorithm. And so this after we use the Thomas algorithm for the computational based. So we want to check the convergence analytically whether we are getting the order 4 or not to match with the computational one. So we are using an analytical solution, convergent analysis for the tridiagonal system. So we are converting the given system into the matrix form. And the well-known matrix theory is used to kind the truncational error, like y of I plus 1, this is yi minus 1, yi plus 1. Using Taylor series expansion, expand it, combine the terms, and find the truncational error for the given problem. So once we find the truncational error, you can find here my at most whatever I'm getting is like truncation error is mh6 by sigma. M is nothing but the maximum order term. What is going to depend on the problem. So my truncational error, whatever the E is nothing but order of h power 4 by epsilon. So the order depends on the epsilon. So epsilon is very constant again. So the maximum order what we are getting is h power 4. The similar analysis can be carried out. So we are doing the analysis for 1 to 2. The same analysis can be carried out for the existing problem from 1 to 2 also. Numerical example is discussed here. We use MATLAB or Mathematica to compute the given problem. So since the problem is we have a delay differential equation model for the delay differential equation, we don't have the exact solution for the given problem. So what we do is we use a double pressure principle. What is the value at n we use for the y of 2n? We find the truncational error for this. So to demonstrate the applicability of the method, we consider the some of the 4 boundary problems consider and compare with the theory already existing. Since the exact solution of the problem are not known, the maximum absolute error is calculated using double mesh principle. The value at yn is known here, so y at 2n we are going to calculate it and find the maximum error what you are getting. and the numerical rate is calculated. So the truncational error, like the rate of convergence, is calculated according to this. So R is nothing but error at n divided by error at 2n divided by log 2. So we'll give the numerical rate of convergence is calculated. So for the first problem, for the first example, you can see here, for the reaction diffusion problem, my A is 5, my B is -1, my F is 1. Okay, and epsilon values, we are going to take epsilon value for a very small value. The epsilon values are varies from 0 to 1. And you can see y of x is equal to 1 for the history function, and y of 2 is equal to 2 for the boundary value problem, for boundary at x is equal to 2. Okay, so using my principle, like for n value and epsilon values, you can see the truncational error, and rate of convergence is almost 4. So these are my error. What is given in the first one is 3.9675 is nothing but the rate of convergence, and what is the error using my double mesh principle. And the graph is drawn between the error for graph for the solution with epsilon is equal to 2 power minus 10. So we cannot able to identify the graph, like, so we have a error, exact solution, and also the numerical solution. Suppose I take some other function, my A is 2, B is -1, and the history function is given. We can have a, we can see here, have a error and also the rate of convergence. So almost my rate of convergence is 4. If I increase my epsilon values, like decrease my epsilon values, I'm getting the rate of convergence is reduced, because my rate of convergence, what I calculate, is order of h power 4 by epsilon. So the rate of convergence depends on my epsilon value. So if I decrease my epsilon value, my rate of convergence affected. So almost I'm getting 4th order convergence. So this is a graph for the given problem. Go for the another example, like variable coefficients. A is nothing but x plus 5, B is -1. With the given condition, with the given history function, y of x is equal to 1 over the range -1 to 0, and y of 2 is equal to 2. So you can, for the variable function also, you can see my error is very less. This error, this problem, already this problem is published in some other paper. We compare this problem with the existing solution of this method. So our method problem is far better than the other problem. So the rate of convergence is 3.9 and 51. So almost it is 4th order convergence. So this is a graph for a given problem, and these are the reference what we done, like comparison of reference. And this is a problem where we have already published with some other methods. We compare this method with our method. Initial value technique is used. We use a numeral finite difference scheme for the reaction diffusion problem, and solution for the difference equation of singular perturbations. And this paper will give you an idea of matrix theory, how you can solve the matrix theory. And thank you. Just I want to give you one more link, how to model a given simple problem. One of the problem setting for any modeling of a problem, an industrial oriented, what we have seen in the previous is a research problem. We are, for a personal stuff, we are solving the research problem, and for already existing problem, we are giving our methods and comparing the already existing method, and we are writing a paper. But if you're going for a problem setting, how the differential equations are used and how it is can be done. So there are a lot of mathematical modeling is done on a industrial oriented problem. This is one of the bottling it problem, bottle problem, where you are going to detect the leakage of a problem. Okay, so these are the problem bottles. It may be any bottle. It may be a drug company or a drug productions where the bottle is made. So once it goes to the leak detector, 92% is accepted, 8% is rejected because there is a uh, problem with the bottle. So what the company want is this 8% they want to reduce it to 1%. Okay. So again you want to go for retest. You want to identify what is the error and retest. So simple mechanism of a industrial problem. You can use this type of technique of problem to model it into the you can model according to that and you can give a solution for the industry which is very useful for the oriented problem. So all the modeling problem which depends in our differential equation, so this problem is modeled according to that. So these are the principle you want to identify to model it. How do we model the process? First attempt is we are working for the company, we are giving a solution to the company to better the company system. How can we generate and what is the schemes we are going to do it? So whenever you go for a modeling of a method or a modeling, it will be in the form of differential equation. It may be a first order differential equation, second order differential equation, and it depends on the time. So if time parameter is there, there will be a retarded system. If there is a delay, if there is advanced, if it takes 5 minutes more, if it takes 5 minutes less. So what kind of type of predictions you can give on the given modeling problems? So that of the difference you can give it for the given any type of problems. So for a given problem, you can give different approaches. One approach is we did. So modeled the process with an ODE, ordinary differential equation, very simple case, and analytical solution to the ODE using artificial company data we are given, and three methods proposed for this given problem. So any type of redundant. So what I'm going to say from this here is, so whenever you take a system, whenever you're getting, you want to take any predicted problem of system from an industry or from a practical oriented problem or for any predictions of data. So now the present scenario of COVID, like how a system is modeled using my COVID system, like how it has happened in the last month and what can be predicted in this month. So you have a past history value. What can you predict using a future value? Okay, so you have a past value. So a lot of research is going on how the problem is modeled using the way the already existing data are there. So you're giving your input for the given data, you're modeling the data using the differential equations. Maybe any class of differential equation using advanced equations or using your delay differential equation, and you are giving your comparison that suppose it happens like 2000 people or 20,000 people are affected last year, what can be happened in the next month if this curve or if this way is going to extend. So that kind of predictions you can give using the differential equations, and there are a lot of existing methods already there, a lot of existing tool is already there to solve the given problem, given differential equation. You can use any one of the form of equation, you can use it any one of the method to solve it. You can find a suitable method which will give you a vast unique solution. The rate of convergence is more and the error is very less. You can give you a comparison and you can give an input for output for the given problem. Like so, this is one of the few example what we have discussed. Delay differential equation with a singular perturbed problem. Now people are working on both. One parameter is singularly perturbed, another parameter is advanced. So how to model that type of problem is very important uniqueness. We can go for some other method instead of numero methods. We can go for any other method, fitted finite difference scheme method, numero method. People have worked on initial value problems, initial value technique method. So there are a lot of methods to solve a problem, but we want the error to be less, conversion rate should be more, and the predictions of output what we have done already should be worst, and it should be acceptable in this current scenario or current range. If you have any queries, you can.
Thank you, sir. I think these informations will be useful for the research people. There's one question, sir. Can you explain perturbed delay differential equation and its application? Hello, sir.
Yes, ma'am, I'm coming. I told you, like, 1 minute, I'll come. Yeah. Everyone is familiar with what is differential equations, like that a system, the equation which depends on a system of one time. But if I come here, the scenario, it is nothing but the differential equations which depends on the delay factor. It's called as a delay differential equation. It mostly occurred with respect to time. So I can give you an example like how it is going to arrive. Like if simple example, you can see my board. My differential equation, first order differential equation, f of y dash is equal to f of x comma y. Y double dash will be f of x comma y double dash. You have your conditions. So these are the simple ODE problems and boundary value problems. Okay. Suppose I consider a differential equation y double dash plus y dash plus y of x minus 1, which is equal to some function f I consider. So I have a delay term here. So this is nothing but a delay. Delay with respect to a parameter of -1 where I have a past history. Suppose I have, like, I'm making a survey of a people of group which has occurred in the last 5 years. I have an article on the last 5 years sampling data. I'm going to take the sampling data and I'm going to predict what is going to happen in the next 5 years. My past value is known. I'm going to make it in the future value. These are the delay problems. Suppose I have a multiplied by a very small parameter. This is nothing but a parameter. Perturbation, we call it as perturbation parameter, where it is multiplied by a second order multiplied. It's called as it's called as a singularly perturbed delay differential equations. This is the example where we are giving a singularly perturbed delay differential equation is a differential equation in which higher order derivative is multiplied. Wherever the control system, wherever the time is required to sense the information, there we are going to play with a delay. So wherever the time is going to happen, there are two things. One, if the time is delayed, what can be the equation be? If time is advanced, we call it as an advanced differential equation or retarded differential equations. So wherever the system is going to find with a time delay problem will come. Where the time is going to lag, time is going to advance, we call it as an advance problem. Okay, so that are the parameters where you're going to have a lot of more application part as there, like in the sense in the modeling of disease problem, control theory problem, and a lot of things we are going to have.
Okay, sir. So there's one more question. Like, what is the status of solution of Navier-Stokes equation as of now?
As of now, the analytical solution is not existing. People went for a lot of computational, like numerical solutions. Now, recently, paper have been published on the Navier-Stokes equations for the assumption method, like on the computational based. People used, scientists use, like people have worked on this using the arbitrary value of giving constants values, and they used mine. So they went for the numerical solutions. The status of exact solution is not yet discovered, like not yet found. They went for the numerical solutions of Navier-Stokes equations.
And sir
Thank you,
has
sir.
said, thank you very much for the presentation. Yes, sir. If there are no more questions, so we will thank the speaker. Ma'am, there's no more questions, I suppose. Shall we thank the speaker? Yeah. I request Mrs. K. Kalpana, Assistant Professor, PG and Research Department of Mathematics, DG Vaishnav College, to thank our speaker.
Good evening to all. The more you express gratitude for what you have, the more likely you will even more to express gratitude for. It is my privilege to propose vote of thanks on this memorable occasion. A warm and sincere thanks to our resource person, Dr. S. Dinesh Kumar, Assistant Professor, Department of Mathematics, School of Advanced Sciences, VIT Vellore, for readily accepting our invitation amidst his busy schedule and enlightening everyone with his thought-provoking lecture on higher order fitted operator numerical scheme for singularity perturbed delay differential equations. Thank you, sir. Last but not least, a special thanks to all the enthusiastic participants across the country who made this national conference a grand success. Thank you all. We will meet tomorrow for day 2 session at 10 a.m. Thank you.